Yeah. So I suppose everyone can hear me. All right. So this talk is on this communication distortion trade-off in voting, and this is based on a couple of joint papers with Debmaya Mandal, who is present here, I believe, who is a brilliant postdoc at Columbia, Ariel Prokacha, who is now a faculty member at Carnegie at Harvard, and David Woodruff, who is a faculty member at CMU. All right. So, so Gerardus already talked about this participatory budgeting setting, where because you have these various different projects that are proposed, and sometimes, as you can see in this map, you might have many different projects that are proposed by the citizens, and then voting over all of these projects can be very cognitively taxing. So you may not want, for example, to ask the participants to just rank all the different proposals. You might want to ask them to report some very concise vote in a very concise vote format. And as Gerardus illustrated, different vote formats might have different associated distortion. And so what we want to really do is we want to look at not only how we aggregate the votes, but also how we design the ballot in the first place. And here the trade-off is between the distortion that this ballot or this input format allows us to achieve along with the best aggregation rule for that input format versus the cognitive burden that this ballot format imposes on the voters. And indeed, if we don't look at the cognitive burden as a separate axis, then we might as well just ask the voters to report their full cardinal valuations, and then we can choose the socially optimal outcome and have a distortion one, right? So the distortion, analyzing the distortion only makes sense if you also look at this cognitive burden axis. So in the sequence of papers, what we do is we take a very crude measure of this cognitive burden, which is the number of bits that a voter needs to communicate by answering this ballot. So just as an example, if you ask voters to rank m different alternatives, then the voter is really communicating m log m bits of information, which is log of m factorial. If you ask the voters to just submit their plurality votes, which is picking one alternative out of m alternatives, then this is log n bits of information. If you ask the voters to submit knapsack votes, which is reporting a subset of the projects, then this is log of 2 raised to m, which is m bits of information. Okay, so this different input formats, they impose different amount of cognitive burden on the voters. And then the question that we want to ask is, what is the optimal trade-off between the distortion and the number of bits that the voter needs to communicate? Of course, the more bits we ask from the voters, the lower we can make the distortion. So another way of phrasing this question is, if we ask each voter to report only k bits of information, so we only have the flexibility of learning about the voter valuations up to k bits, then how much can we minimize the distortion? And in particular, what kind of k bits do we want to ask for? What is the optimal ballot with this budget on the communication? So one thing that I want to make clear here is that in the entire talk, I'm going to look at a kind of ballot that is common to all the voters, right? So you are not going to ask one voter to rank all the alternatives, all the m alternatives, but ask another voter to only report his top 5 favorite alternatives. Okay, so you are going to design the ballot, but then you are going to ask all the voters to report with regards to this ballot. All right. So here we are not going to look at the participatory budgeting setting. We are going to come back to the standard voting model where you have n voters, you have m alternatives, and the voters have this valuation function which is normalized over the space of alternatives. So the voter I has a value vi of a for each alternative a, and then the values sum to 1, as you have seen throughout this workshop. So another way of saying is that the voter's valuation function lies in the m simplex. That's what I'm going to denote as delta raised to m. And then the social welfare of an alternative, as you have seen, is just the sum of the values that different voters place on that alternative. So I'm not going to spend too much time on this model because you have already seen this. The one key distinction from what you have seen so far is that now the voting process is going to be broken into two stages, because we have not only the aggregation rule that we want to design, but also the ballot that we want to design in the first place. So you have the voters in the black here, and they have some valuation functions over, say, 3 alternatives. And these voters are going to use some elicitation rule. So there is an elicitation rule that decides what the ballot is going to be. And the voters look at this elicitation rule and accordingly create the responses, row 1, row 2, and row 3. So these are the, think of them as very concise representation of the voters' valuation function. So these could be rankings over the alternatives, or this could be just the top 5 alternatives, or this could be something more general. So the voters are going to use this elicitation rule to convert their valuations into very succinct representations, these responses, and then these responses are going to be passed to this aggregation rule, which is then going to spit out a winning alternative. Yes, so we are in the standard voting setting where we want to just pick a winning alternative, and there are no costs to these alternatives. There is no budget constraint. All right, so technically, with each voting rule F, we have 2 rules associated. One is the elicitation rule that just maps a valuation from the simplex to a finite response space, right? And the number of bits that is elicited by doing this is the log of the size of R. And once each voter maps its valuation vi to this response rho I according to this function, then all of these responses row 1 through row n are passed to this aggregation rule, which then spits out a winning alternative. And the key thing here is that both this elicitation rule or the aggregation rule can be either deterministic. So you can just pick a function and call it the elicitation or the aggregation rule, or you can choose a function at random. So maybe you can say that with probability half, this is going to be my ballot. With probability half, that is going to be my ballot. But note that you have to fix your ballot. So you have to sample your ballot from the probability distribution and then fix it, and then have all the voters respond to the same ballot. And the 2 metrics that we are going to compare, this distortion and communication complexity. So the communication complexity, as I already said, is the log of the size of R, which is the range of this elicitation rule. And because we allow sometimes the elicitation rule pi f to be randomized, we might have to take expectation over this quantity. So this is the expected number of bits elicited from each voter. And then distortion is same as before. The only reason that you see a slightly more complicated formula here is that I'm first taking the voter valuations v1 through vn. I'm applying the elicitation rule pi f on top of that, collecting the responses, and then submitting that responses inside the aggregation rule gamma f, and then looking at the social welfare of the winner that's picked. And here again, you have to take the expected social welfare if either your aggregation rule or elicitation rule is randomized. Okay, so so one thing that I want to point out here is that we already know some of the results from the literature. So for example, we know that if you ask voters to report rankings over alternatives, full rankings, then with m log n bits of information, you can get roughly square root m distortion. So I'm not going to go over all these past results from the literature, because those results, it will turn out, are Pareto dominated. So those results are not optimal. And I'm instead just going to directly present the optimal voting rules that, subject to a budget constraint, achieve the best distortion, or equivalently, subject to a desired level of distortion, they ask for the fewest number of bits from the voters, asymptotically. All right. So I'm going to look at 2 separate cases. The first is the case where you want your elicitation rule or your ballot to be deterministic. So you just want to find a ballot, fix it, and then ask the voters to answer this ballot. So in this case, what we show is that this prefix threshold or pref threshold rule is asymptotically optimal. And this, the elicitation rule for this, this voting rule is very simple. So what you do is you take this interval 0 to 1, which contains the voters' utilities for the different alternatives, and you divide it into roughly log m exponentially spaced buckets. So the first bucket is just 0 through 1 over m squared, and then you just double every time. So 1 over m squared to 2 over m squared, 2 over m squared to 4 over m squared, and so on. And then each voter, I, not only reports her top M over D favorite alternatives. So note that D here is the distortion that we want to achieve, and M is the number of alternatives. So what you do is you ask each voter to report her top roughly M over D alternatives, and not only that, for each of those alternatives, you also ask the voter to identify which bucket contains her value for that alternative. And it's easy to see that the number of bits that are elicited by this elicitation rule is roughly M over D. I'm hiding some logarithmic factors here. Okay, so throughout the talk, I'm not going to pay attention to logarithmic factors. I want to achieve optimal bounds up to log factors. All right, so the elicitation rule, I hope, is clear. Now, how do we aggregate these kind of votes? The aggregation rule is very simple. Every time a voter I says that this alternative A is in my top M over D alternatives, and my utility for it say lies in this bucket 1 over n squared to 2 over n squared, you just take, say, the upper end point 2 over n squared as your estimate of the value of this voter for this alternative. And for every alternative that the voter doesn't report, just assume the voter's utility is 0. And using these estimated values of the voters for the alternatives, you compute the estimated social welfare of each alternative and just deterministically pick the alternative that maximizes the estimated social welfare. Okay. So basically, you are just going to listen to the voters and pick one that seems to have the highest social welfare based on what the voters say. So note that the aggregation rule that I'm using here is deterministic. And what we show is that with this particular rule, you can actually establish that this voting rule has distortion order D. Okay, so it has the desired distortion, and it uses only roughly M over D bits of elicitation. And later in the talk, I'm going to show that this is actually optimal. And it's not only optimal for deterministic aggregation rules. Even if you had the flexibility of using a randomized aggregation rule, you cannot really outperform this. So it turns out that when you are using deterministic elicitation, using a randomized aggregation rule doesn't really help achieve any better distortion than using a deterministic aggregation rule, as long as you are using the best elicitation rule. So I'm not going to walk through the proof of this, but the analysis is not that complex. The situation gets a lot more interesting when you go to randomized elicitation rules. So here we make connection to this idea of sketching and sampling from streaming algorithms literature in theoretical computer science. And specifically, we look at this notion of perfect L2 samplers. So this was introduced by Nisarg and Woodruff in 2010. And the idea is the following. Let's say you have an m-dimensional vector x, and there are some updates that are coming to x. So these updates are changing the coordinates of x, and you want to process these updates. And once all the updates have ended, you want to run some algorithm which with high probability 1 minus delta outputs a random coordinate j hat, such that each coordinate j is picked with probability proportional to roughly the square of x of j. Okay, so you want all the different coordinates being picked with probability proportional to the square of the value of x at that coordinate. Now, of course, if you just use order m memory and you just keep the entire vector x in your memory and just keep processing all the updates, then at the end you can very simply just do this sampling process. But the idea here is to do that with low space requirements. So you don't want to actually use order m memory. You want to use lower memory than that and somehow still be able to do that. Now, of course, with less amount of memory, you won't be able to do this exactly. So we allow some small polynomial error in this probabilities. And very recently, Jairam and Woodruff showed that there exists for this such perfect L2 samplers that have low space complexity, that use the so-called linear sketches. And this is something that will become clear in the next slide. And the last property, crucially, is that they don't only just produce a coordinate j hat, they also produce an estimate of the value of x at that coordinate, which is x of j hat. So they produce, say, a constant factor approximation of this quantity. And so this is also going to be very useful in our voting. All right, so how do we use this idea of sketching and sampling to design a voting rule with randomized elicitation? Well, so you have these voters and they have their valuation functions, v1 through vn. the idea is that we want them to send some very succinct representation of their valuations to the center. And so here we are going to use the sketch function, say h, and each voter I is going to send h of vi, which is very succinct to the center. And the fact that h is linear, so recall that I said that the sketches that they use are linear. What that means is that if you just add up h of v1, h of v2, h of vn, then what you get is the sketch of the sum. So the sum of the sketches is the sketch of the sum, but the sketch of v1 plus v2 plus vn is simply the sketch of the social welfare function. And then when you sample alternatives according to this sketch, what you are really doing is you are sampling each alternative with probability that's roughly proportional to the square of the social welfare of the alternative. And so the nice thing about this is that alternatives that have high social welfare are going to be picked with very, very high probability, right? Note that it's not just proportional to the social welfare, it's proportional to the square of the social welfare. So as the social welfare of an alternative increases, the probability that it's picked increases much higher. And so this is going to be crucial in deriving the distortion bound of D. Okay, so ultimately we want to use the fact that we can sample alternatives with probability proportional to the square of the social welfare in order to get low distortion. And then the low communication complexity will simply come from the fact that this sketch uses low memory or low space requirement. Now, there is one caveat here, which is that the sketches are typically designed to operate on integral inputs, whereas what we have here is real valued inputs. So we can't directly ask the voters to send the sketch of their valuation functions. Instead, what we need to do is we need to ask voters to round their valuations first. So we pick some large number delta, and then we ask the voters to round each value that they have for each alternative up to the nearest multiple of 1 over delta. Okay, so now the number of bits contained in the rounded valuations becomes finite. And then we ask them to send a sketch of this rounded valuation function. But instead of asking for just one sketch, we are going to ask them to send order m over d cube independent sketches of this rounded valuation function. Okay, and this is because in the aggregation rule, when we add up all these sketches, we want not just one sample of the alternative with probability proportional to the square of the social welfare, we want m over d cube independent samples. Okay, and this is just a boosting idea. Essentially, if you have these many independent samples, then you can show that the best sample out of that is going to be low distortion with very high probability. Okay, so the key property that we use here is the third property of the L2 sampler of Jairam and Woodruff that I mentioned earlier, which is that it not only produces a random coordinate j hat, but it also produces an estimate of x of j hat. So here we not only get an alternative sampled at random, we also get an estimate of the social welfare of that alternative. And so then once we have this m over d cube random samples of the alternatives, we just pick the alternative that has the best estimated social welfare and return that. And so again, here the elicitation rule is randomized because this order m over d cube independent sketches that we want the voters to send us, we have to generate the sketch functions at random and then make that part of the ballot. So we sample random sketch functions and then we say that here is now our ballot. You send us the sketches of your valuation functions or rounded valuation functions according to the sketch functions. And the aggregation rule is still deterministic. And here again, it's not very difficult to show that up to logarithmic factors, the communication complexity is m over d cube. So basically per sketch, we only need logarithmic bits of information from the voters. And then we have these many sketches. So that's the communication complexity. And the key kind of analysis in this part goes into showing that once you have these m over d cube independent samples of alternatives picked with probability proportional to the square of the social welfare, the best of them will actually give you distortion order D. Okay, so with that, let me move on to the lower bounds. So one thing I want to emphasize here is that you don't only want to prove a lower bound on a particular input format, as most of this literature on distortion does, here we want to prove lower bounds across all possible input formats that you can ever imagine. Okay, so what you want to show is that any input format that helps you achieve distortion T must have communication complexity at least M over D or M over D cube, depending on whether it's deterministic elicitation or randomized. And so the reason that this is complex is because you can imagine very, very complex elicitation format. A k-bit elicitation format essentially just partitions the simplex into some 2⁻k compartments and then asks the voter to identify the compartment that contains its valuation. So there are infinitely many possible elicitation formats with any fixed complexity k. And then we want to kind of prove a lower bound across all of these possible input formats. All right, so to do this, we make connection to this literature of communication complexity from TCS, and particularly to this classic problem of multi-party set disjointness. So here, imagine that, so forget all about voting for now. Imagine that there is a set U, a universe U containing some M elements, and there are T players, and each player I holds a subset of the universe, call it SI. As the name of the problem suggests, the goal is to find out if the sets that are held by these players are pairwise disjoint or not. Okay, so the players want to find out if their sets are pairwise disjoint. Now, of course, they can just declare the sets that they hold, and then they can just check pairwise comparison, pairwise intersection, but this would require them to communicate their entire sets, right? And which would be order M amount of information. And we want to solve this problem with fewer bits of information communicated from the players. And so classically, this problem is analyzed under some kind of promise. So some omniscient entity comes to you and says that, look, I guarantee to you that the problem that you are facing will only be of one of two types. Either it will be a no instance, where the sets held by the players are in fact pairwise disjoint, or in the other case, where the problem is a yes instance, not only do you know that these are not pairwise disjoint, but in fact, I'm going to tell you a lot more. I'm going to promise to you that there is going to be some element X, such that this element X is present in all the sets, and other than this element X, the sets are going to be pairwise disjoint. Okay. So note that the yes instance is not just a negation of no instance, it actually has a lot more structure built into it. And the more that this promise, the more structure that this promise gives you, hopefully the fewer amount of bits that you need to ask the players to communicate in order to find out whether it's a yes or a no instance. All right, so the question is, subject to this promise, how many bits do we need the players to communicate before we can figure out whether it's a yes instance or a no instance? And so here's a pictorial representation. You have these players and they hold some sets privately, and they want to figure out if the sets are pairwise disjoint or not. So here, this is actually a yes instance because the green element is present in all the sets, but other than that, the sets are pairwise disjoint. And the way that this is analyzed is in this shared blackboard model, where there is a protocol, and this protocol goes to one of the players, asks the players to write a particular bit of information about the set that she holds. So the player writes this on the shared blackboard. All of the players see this, and then depending on this bit, now the protocol can ask a different player to write some bit of information about her set. And so the players kind of take turns writing some bits of information on this shared blackboard, which is visible to everyone, about their individual sets. And at some point, the protocol says, you know what, the information that is already written on the shared blackboard is enough for us to determine that the instance is a yes instance. Right? And the quantity that you want to bound is the total number of bits that must be written by all the players combined on the shared blackboard before you can answer yes or no. Okay? And you want this, you want to bound this quantity in the worst case over all possible instances. So before we directly use this, we actually needed to introduce a variant of this problem, a special case of this problem, and show that that problem also remains hard. Okay, so what we do is we create this fixed size variant of the set disjointness problem, where we further impose this restriction that the sets held by the different players have the same size S, which is known to us. And what we are really going to show is that this restriction doesn't really make the problem any easier. Even though you know this, you still need to write roughly as many bits as before in order to solve this problem. Okay, so what do we know about this problem from the communication complexity literature? Well, it was known that if you have any randomized protocol for solving this problem, which only makes some delta error, so with probability 1 minus delta, it will give you the correct answer. Then, if you have m elements and t players, you need the players to roughly communicate at least m over t bits of information on the shared blackboard before you can find out the answer. So what we first do is we reduce this problem to the fixed size set disjointness problem, and we show that even when you know that all the players' sets have the same size, which is roughly m over t, the problem doesn't get any easier. You still need to write m over t bits in order to find out the answer. And then we reduce this to the voting problem, and we show that if you have a voting rule f that achieves distortion d, you can actually use this voting rule to solve the the fixed size set disjointness problem. And because we already have a lower bound on the fixed size set disjointness, we can actually derive a lower bound on voting. And if you run through this not very difficult reduction, what you get is that if the voting rule uses deterministic elicitation, then the communication complexity it has must be at least m over d squared. And if it uses randomized elicitation, then its communication complexity must be at least m over d cubed. Okay, so note that the m over d cubed lower bound for randomized elicitation is already optimal. And the upper bound that I showed you earlier does in fact achieve m over d cubed communication complexity as an upper bound. So whereas the deterministic elicitation lower bound is not that. The upper bound was m over d, the lower bound is m over d squared. It turns out that this particular framework is not sufficient in order for us to derive this m over d lower bound. So for that, we actually introduce a new type of promise that we call substantial intersection promise. So the no instances are same as before. In a no instance, the sets of the players are pairwise disjoint. But in a yes instance, now you know a lot less structure than before. Okay, so before I told you that in a yes instance, there is an element x that is present in all the sets, and other than this element x, the sets are pairwise disjoint. Here, all I am going to tell you is that there is at least one element x that is present in at least a constant fraction of the sets. Okay, and other than that, I'm not going to tell you anything. So, for example, there could be several different elements x that are present in at least a constant fraction of the sets, and other than that, the sets may not even be pairwise disjoint. They may have some other intersections as well. So this is a weaker promise than the unique intersection promise, and because we have a weaker promise, we can hope that the players might need to write more bits on the shared blackboard before they can figure out the answer. And indeed, we show that if you have a deterministic protocol for solving this problem, this fixed size set disjointness problem, and this deterministic protocol is not allowed to make any error with any probability, then the players must write at least omega of n bits on the shared blackboard. So note that this is an improvement over the previous bound of m over t, but we are only able to prove this for deterministic protocols. It turns out that that doesn't matter. The reduction that we use for voting rules to deterministic elicitation actually creates a deterministic protocol to solve this fixed size set disjointness problem. So we can actually use this improved lower bound here to get an improved lower bound on voting rules to deterministic elicitation, and we can show that this m over d is in fact optimal up to log factors. All right, so the moral of the story so far is that if you want to achieve distortion roughly d, then the communication complexity that you need is m over d if you use deterministic elicitation, and m over d cubed if you use randomized elicitation. And the nice thing here is that we actually establish a connection to two different literatures from TCS, the communication complexity and sketching and sampling. And in case of communication complexity, it's actually a bidirectional literature. Not only did we use results from this literature, we actually derived new results in this literature, like this substantial intersection promise or the fixed size set disjointness variant of the problem, which were then helpful for us to design better lower bounds on voting. So these results might be of independent interest in this community. For sketching and sampling, so far we only used existing results from this literature, but it remains to be seen whether new developments in voting require new results in this literature. Okay, before I conclude, I just want to mention that we also look at this problem of K selection, which is where you want to select a committee of K alternatives rather than just selecting one alternative. And the value that a voter derives from a committee, you assume that the voter basically connects to the representative in this committee that she likes the most. So her value from a committee of alternatives is the max of her values for the individual alternatives in the committee. And now you want to select a committee that optimizes social welfare, or rather you want to minimize distortion. So a priori, it is not even clear what happens to the problem as you vary K, because as K increases, certainly you have the flexibility to pick more alternatives, which is useful for getting higher social welfare, but the optimal also picks more alternatives, so the optimal social welfare also increases. So it's not clear whether the distortion is going to be improved or worsened when K increases. So what we show, we also get tight bounds for this setting. We show that, and using very different techniques, because it turns out that techniques from the one selection problem, many of them don't actually work for the case selection problem. So using different techniques, we show that if you want to achieve ordered mean distortion, the optimal communication complexity that you need in both cases falls linearly as K increases. Okay, so the problem actually does get easier as K increases. All right, so just to end the talk, some mention of high-level future work. So first of all, as I said at the very beginning of the talk, this communication complexity is just a crude measure of cognitive burden. Of course, you need a more social science kind of approach here, where you actually measure the cognitive burden imposed on the voters by the different voting formats. And so here with some collaborators, we did some preliminary experiments to judge the cognitive burden imposed by the 4 input formats that Herdus mentioned in the previous talk. And our high-level conclusion was that the cognitive difficulty roughly matches the number of bits that are elicited, except ranking by value for money is much harder than ranking by value. So certainly, number of bits is not the appropriate measure for cognitive burden. We need more research in order to understand this more deeply. And also, there are some intangible effects of ballot design which don't have a nice theoretical analog. So for example, at some point we were talking to the participatory budgeting team that is responsible for PV elections in Barcelona. And what they said is that even though the knapsack votes may be very bad from the perspective of distortion, as Herdus said, they lead to exponential distortion in the deterministic aggregation case, and basically same order M distortion in the randomized case that you can get with no information. They are still very good from a psychological perspective because they help voters understand the limitation imposed by the budget. So for example, if you just ask the voters to take all the alternatives for which their value is at least some threshold, then the voters might end up picking a lot of different alternatives. And then at the end, when the city only implements 3 or 4 of these projects, the voters might be frustrated thinking that the city is not doing its job correctly. Okay? Whereas if the voters have this budget in front of them and they try putting different projects into a bucket and they see how quickly the budget fills up, the voters might realize that, look, if you want really good projects into this knapsack, then you are only going to be able to put 3 or 4 projects in it before the budget fills up. Okay? So it kind of helps voter understand the impact of the costs in the budget. All right, so these are the references. These 2 papers were published in NeurIPS 2019 and this year EC 2020. Okay, thank you.